Hello and a warm welcome back. Today on the bench is the Class Limited of London 200 watt per channel Lateral Mosfet amplifier, and this is the non-working channel. The other channel works, but as you'll see later, works is, yeah, I've had a hell of a job to try and get this far because of the BJT stage. Essentially this is a direct coupled amplifier, which makes it far more difficult to fault find than an amplifier like where you get on a valve amp where you've got capacitors joining in individual stages. Let's have a look at the schematic. This is about the third or fourth time I've drawn the schematic, and I still didn't get it right on this last attempt. So basically this feedback RC network goes here to the emitter here. So let's have a look at the schematic and try to make sense of it. The reason I've been really struggling with this amplifier is because I don't really know what the hell I'm doing. I sort of do, but I don't. Valves is more my thing. Three-legged fuses, bit difficult for me. Anyway, so the problem I've had is trying to get these two transistors here working properly such that they drop the correct voltage across this 10k resistor here and thus bias the MOSFETs on properly. I've had a lot of help from the lads on the forum, and a chap on there has run the simulation and thinks for LT Spice, and he thinks this is a Class B amplifier, not AB, Class B. So essentially what happens is you've got this ZTX 653 here, and you've got a 10k resistor here onto the positive rail here, negative rail down at the bottom, and that ZTX 653 is connected across there. So essentially this, forget the diode, this 10k and this ZTX 653 perform are a potential divider. If enough current, if just the right current flows through this transistor here, then we should get about 0.5 volts here on the NFETs, on the N channel lateral MOSFETs. The problem I've had is that every time I've tested this, and I've tried lots of different transistors, I tried MPSA 4292 pairs and all the rest of it, but no, you need just the right transistor here with the right current gain and all the rest of it, otherwise the circuit won't work. It's also complicated because, like I say, it's in a closed loop situation, so it needs, basically this stage here needs the correct voltage here going through the feedback network to function correctly. The other problem is we need a similar sort of transistor here. We need a high voltage because potentially we've got 100 volts across the resistor, and also a high gain transistor. And so I've had a bit of a devil trying to find a transistor that works. I might have said resistor instead of transistor there. You try describing it, try it sometime. And so essentially this NPN here transistor is self-biased by this 2K7 resistor, and that biases it either on just enough or not enough. But to complicate matters, it's connected, the base of this NPN is connected to this PNP collector here. Now, as you know, or some of you may not know, a PNP transistor works a bit different. See the arrow? Current flows into the base on a PNP, and it flows out of the base on an NPN. So what we get here on this collector of this PNP transistor will affect the bias voltage of this NPN, because if there's too much current flowing, then it's going to turn hard on and we're going to get a negative voltage up here, like, which is what's been happening, or it can just turn it off completely and we'll just get like plus 45 volts here. Yeah, bit of a nightmare. I don't particularly fully understand the circuit 100%, but we're getting somewhere, so you'll see later. And then this PNP transistor is basically our voltage amplification stage. Our input comes in here onto the base, blah de blah de blah. And then also, to further complicate things, having looked into lateral Mosfets a bit more and done a bit more research, all Mosfets are pretty notorious. In fact, all transistors are pretty notorious because they have such a high gain up to frequencies like into the VHF, some of them, you know, very high frequency, then they're prone to oscillation. And that's why we had, if I can find the damn thing, no, I'll put it away. That's why we had that burnt out Zobel resistor on the good working channel. So essentially we've got to have just the right transistors here for the whole thing to work, and it's a bit of a nightmare trying to sort it out. It's a bit like a seesaw, you know, you get a fat bloke on one end and a 3-year-old kid on the other end, and it's not going to work. Anyway, I'll shut up waffling now and show you the rest of the footage where I start to get things sorted out. Prior to this, I've got about 5 hours of footage which you don't want to see of me like floundering around and fucking up. Yes, as you can see, this non-working board is in a right fucking mess, and it's really been, and still continues to be, a challenge. And it all basically centres around these two BJT transistors that form the voltage amplification driver stage, and I'll get into that in a minute. Today's the 6th of November 2024, and it sounds like, and this is the last time I'm going to mention politics for a while, it looks like President Donald Trump is going to win the USA elections, potentially because he's such a bleeding idiot and unstable and just, yeah, fucking moron. It could really affect all our lives, because if he starts pulling like funding to the Ukrainians, the Chinese might get emboldened and invade Taiwan. If they invade Taiwan, then we could potentially have a nuclear fucking war. So yeah, at this time in the, you know, the state of the world affairs, we need a steady, sensible hand at the, you know, at the controls, like in the fucking USA. He isn't that, and that's the last I'm going to say on the subject. Let's just say he doesn't win. Anyway, so that's the amplifier. As you can see, it's in a bit of a bleeding state. I've been working on it pretty much every morning, the odd few hours here and there for a week. So the chaps have suggested, well, okay, what could be happening is it's oscillating. So what the chap suggested I do is get the good channel working and probe for oscillation. I did probe for oscillation, parasitic oscillation, earlier on when working on this board. Yeah, and so at the moment I don't know what the fuck I'm gonna do with that duff board, and so I suggested I'm gonna put this into its heatsink. I've got some replacement pots somewhere, which I suggested to Rob because the old ones aren't the best, and so I've got some decent Bourne's pots, and they've got longer legs on them, and so I'm going to do that, pop it in its heatsink and do a little bit of testing, and yeah, just see how it sort of how it goes and take it from there. And then at some point I'm going to go and have to try and tackle that bloody Duff amplifier as well. Here we are the next morning. I've managed to solder the volume pot in. It looks well done, it's nice and blue and lovely, but this pot is like far better than the old one. Got it rough, it's not in tight. And then next I need to insulate these output devices. I'm very fortunate to have sheets of new old stock mica. This is quite thick stuff. I think that's a bit of plastic. As you can see, I've got various sheets. It's not like a plastic, it's very hard. As you can see, when you cut it, it shears. And yeah, see, look at this, look, isn't this beautiful? Used to sell this for cookers and things. I don't know, when was this from? Way back when. So yeah, I've got some lovely old sheets of mica, but I'm not going to cut those up just yet because the whole project hangs in the air. And so I'm going to just use some plastic sheet that I saved from packaging. I don't know, this probably came off some Christmas cards, which will do in the meantime for testing. It's not brilliant for, you know, transferring heat into the heatsink, but it's better than now, and I'm not going to be testing it at high powers anyway. So let me go and do that, stop waving it about, and I'll catch you in a minute. So that's the good working channel, loosely put in. The output devices are screwed down. At the moment this 3mm M3 bolts in there, but I've been trying to fit the 4M4 bolt that came with the amp into here. I realised it isn't metric threads and all the rest of it, it's BA. So I found a whatever BA it is, 4BA. So next thing, before we can go gallivanting off into the sunset testing it, is to make sure that none of these output devices are shorted to the, where do you call it, heatsink. So I'm just buzzing it out using my meter on continuity. They're all okay. Got no ground to got no ground connection to heatsink either. Positive? No. Right, okay. So we're cushy there. And as you can see, I've brought out some leads. These are for the power connections, DC power connections, rather than using these. I hate these things anyway, so I'm just going to be using those just for this purpose of this test. Well, the good output stage is connected to the power supply, powered on. I've still got the limiting resistors in though. At the moment it's pulling 44 milliamps on the positive channel. I've still got it on the lamp millimeter. I'm really very wary about powering this up full power. I've got it on the scope as well. I'm scoping the output, both lamp limiters out. The current has fallen to 39 milliamps. These are original Semilab BUZ 901, 906p Mosfets. You can't get these anymore, they're real as rocking horse shit. And this design is very minimal, as you can see, and as I mentioned previously, by this burnt out resistor here. That takes a lot of, you know, anyway. So the next thing to do then would be to power it up without the limiting 100 ohm resistors, but for that I'm going to bung it back on the lamp limiter. So I'm going to turn it off, jumper those out and power it up again. Right, jumpered out those two big 100 ohm resistors, still on the variac and lamp limiter. Obviously I can't monitor the current really anymore, although I could do it if I wanted to, but just monitoring the power rail. I'm only going to bring it up to 45 volts. Right, I've got it at 41 at the moment. Just going to switch out one lamp limiter bulb. Just knocked it up to 42.5. That's knocked it up to 43. I've got no oscillation, so I'm just going to pop that up to 45. Well, I've got 44.6, but that's going to rise, I think, over time. Right, just point you at the screen and let's pop in a signal. So we've got a 300 millivolt sine wave. Just going to pop it up to about 3 watts, which is about 6 volts RMS. Let's just leave it at that. Feel those FETs. FETs are okay. Remember, they've got no heatsink. I've got 2.8 volts RMS. 4 volts. Everything's good though. I can feel the heatsink getting warm, and at this point I'm just going to check THD. Now the THD is quite high actually, it's at 0.4%. See how flat it is. I've got, if I just fill the screen with that and use my variable control, right, we need to reduce that further. Right, so we're at 1 kilohertz. Let's bung in a 20 hertz frequency. 20 hertz. Oh fuck's sake, wrong thing. Okay, as you can see, that is surprising. That has really surprised me. That has fallen, not quite by half. That has fallen. So really this amplifier isn't very good in terms of frequency response. So where we're at 448 and it's fallen to 2.3 volts RMS. Frequency 20 kilohertz. And as you can see, that's fallen as well. That's far from our typical, our sort of center frequency in inverted commas at 1 kilohertz. So yeah, it's not a brilliant performing amplifier. I think though, I suspect that this is why the owner likes the sound of it, because it's rich in harmonics and whatnot. Yeah, 0.7% there. Let's just have a look at the 20 THD at 20k. Oh no, frequency 100 hertz. A little bit better there. yeah, 0.3 there, so there is some distortion at high frequencies. So next let's bung in a square wave, and this is what the chaps wanted me to do on the forum, so I'm going to switch off and set that up for a square wave input. So as you can see, we've got some low frequency roll off. I've got it on one half of the lamp limiter at the moment, just in case it takes off. This is at 1 kilohertz. Let's just turn that up a bit more. As you can see, we're starting to, hopefully you can see, we'll zoom you in a bit more. We've got a little bit of sort of ringing there, but nothing heavy. Let's see what it's like at 100 hertz. Yeah, and as you can see, pardon, right, as you can see at 100 hertz we've got extreme low frequency attenuation. Try it at 10k, and as you can see it's gone down, and it's not actually that bad. I was expecting a lot of ringing, but let's take it up a little bit higher. Frequency 20k. Yeah, and we're starting to get some high frequency attenuation, but no real ringing. Let's try it at higher output. Yeah, and it doesn't really start taking off, so it is stable. Well, it's a lot more stable than what I thought it would be, is what I'm trying to say. So I shall report that back to the chaps.
Now is the time for ice cream. Ice cream time. It's ice cream time with Lion's Mate. Ice cream time with Lion's Mate. When Master Maze meets Blondie Butter, wham! It's Butterkiss. Butterkiss on sale now.
Here we are, another morning, lunchtime. As you can see, I've repaired some tracers again, and these are the main ones that do need sort of repairing just now to try and get this BJT stage working. So yeah, repaired that. This is the positive rail here that goes there through this 10k resistor there. The resistor drop, see, and then that goes from there to there, down there, through a diode, through there to, I think it's the emitter of, and I've got the ZTX 653 back in, and then I've fitted a, what have I fitted? A BC556 PNP. This is the last time I'm doing this because I can't really spend any more time on it, especially if I'm getting nowhere. So it'll either get passed on to somebody else who wants to have a go at it, or I've got a few other suggestions for the owner of the amplifier. Sorry, that's really out of frame, isn't it? So let me just check that all my connections are good, then we'll reconnect the power supply and power it up one last time. After a few fits and starts, after making sure that the base of the ZTX 653 NPN transistor was actually making contact with this trace, and mucking about and whatnot, I started heading in the right direction. So I'm going to point you at the meter. What I'm going to do is power it up. I'm going to call you out what the voltages should be on the various parts of the circuit. First I'm going to power it up. Still on the lamp limiter, still with the resistors. You can see over on that one we're pulling about 70-80 milliamps. Let me just make sure I get my voltages. I'm just setting it all around 45 volts at the moment because this is where I've been testing it. I don't want to go any higher than that. Right, okay, we're about 45 volts, plus minus 45 volts. So, make sure I've been this close to this board, I keep forgetting what I'm doing. And right, collector. So the first one we should have is the important one, is this junction of R11 D1. That should be at 0.5 volts. It isn't. Boo hoo. Next, let's make sure we've got collector voltage correct, which should be minus 45. Correct. Now the base voltage is the important one. Let's make sure the base voltage is right. It should be minus 40. Oops, minus 42. Okay, it's not far off. Minus 44. Importantly, I need to make sure that the base voltage of the PNP transistor is at or about 0. It is 0.1. Far out, because in the past that's been at minus 25 volts. And we should have on the emitter, we should have on the PNP, we should have 0.6. Okay, that's good. That's about right. 0.7. Right, but there's one thing I haven't tried yet. This BJ circuit here, as mentioned, I don't know whether it'll be in the editing, but it isn't in an open loop condition, it's in a closed loop condition. So if you can see, like from its emitter of the PNP, that goes through this RC network here, goes back, and then it joins the source of this Mosfet, the N-type Mosfet over here. So we need to make sure that, you know, we've got like sort of the right conditions for this to work. If that ain't right, this ain't gonna work. But there's no Mosfets in at the moment. So to try and make sure that this circuit here is working, I'm going to take this connection here and I'm going to connect it to the junction of this 10K here to this point here. Let's try that. So I've just soldered that in. This is the acid test. After this, if it doesn't work, I'm done. Nothing more I can do. So remember, the important voltage is 0.5 here at this junction here. Pop it on. See if that's made any difference. We were getting minus 44 before, we should have 0.5. If I point you at the meter, look at that. We're getting less than a volt. We're getting 100 and yeah, about 100 millivolts. Fucking brilliant. So that means that our BJT section circuit is working correctly. I've been trying to do this for a freaking week or more, you know, on and off like most days. To get this far is a monumental like achievement, but we're still not out of the woods yet. Obviously we need to fit some Mosfets, and traces around here are still a bit dicky. So I've got like a bag of FETs here, a few in here. Pretty damn sure that these P-FETs, and these are lateral FETs, are okay. So what I'm going to do is try fitting a pair of FETs, 1P, 1M, N-type. I don't know why I keep saying M. 1P, 1N type, and see what that does. I do need to make sure that I put the N-FET in the right place though, because of that feedback connection which is there. So I need to put the N-FET in this position, and the P-FET doesn't really matter so much. Let's give it a go. This is the acid test.